to answer this question. Now let's go to another example problem. Example problem 2, today's class to solve. So this is very interesting problem now, wherein I'm going to explain you this problem from that concept what you learned in the last class called the relative motion concept. Right? So look at now this, what I draw is a bar which is inclined 20 degrees to horizontal. This is a bar which is inclined 20 degrees to horizontal. This is 20 degrees horizontal, and this end is A. So this is horizontal surface, and here maybe this is smooth surface. We can consider there is no friction. We do not account now our force which causes the motion, right? So this is end A on surface A, and end B on surface which is inclined surface 30 degrees to horizontal. So if I extend this, this will meet, right? So this is 30 degrees horizontal. So now the length of this is 2 meters. Or AB length of AB is 2 meters given, and the orientation now shown 20 degrees. The bar is 20 degrees to horizontal. That's the orientation of the bar. But the status of this bar is not. It is supported. It's guided to have a motion. It is not under static equilibrium, because it's a smooth surface. This is also a smooth surface, so its own weight would make this to slide. So this point will translate A motion. Point A motion is translation in horizontal direction. Point B motion is translation in along the slope. Whereas the rigid body AB, when you look at, it is not only translating, it is also rotating. That's what you have to see. The point in a bar, if you look at one point in this bar, if you look at, it is translation. But if you look at all points put together as a bar, as a rigid body, then it is translating as well as rotating. That's what you have to understand. So if that is so, what is the given data is, for the given configuration at that instant, the velocity of point A is given, known. So this velocity VA is given by 3 meters per second. This is 3 meters per second. 3 meter per second. That's given. And velocity of B, we do not know magnitude, but you know that it is being guided on this. So the direction of that is this VB. The direction only I know. So now what would be the question? The question is here, determine the angular velocity of this bar. Angular velocity of this bar. So you should understand there is a rotation of this bar, right? That is what is important. See, what would happen if I do not have any resistance here? It's a smooth surface contact. So this next instant 20 degrees is going to reduce further. It is become 19 degree, 18 degree, 17 degree, and one point of time this is going to be 0, and this entire AB is on the floor. B point would come on this. So that's what is where it will stop. Maybe it will take some time and then it will stop, or it is very slowly coming than this. So as this point B move translate here, A translate into the left, B translate along this, there is an instant when this 20 degrees becomes 0, then it is all are translating. So with a common velocity. But till then, you see this point velocity is different, this point velocity is different, because as a whole, this bar is not only translating, also rotating. That's what you have to see. And this motion is what is called the general plane motion, GPM. That's what I was telling. So how do you solve now this problem? So you're asked to get this. Also, you have to find out what is the velocity of point B, right? And this motion is what is a complex motion, because this can be looked at in an IC engine example. The connecting rod motion will be similar to that of this. We'll see that in a while. So now, do you have understood the question? The question is a bar AB of 2 meter long slides down the plane as shown. The end A slides with the velocity of 3 meters per second to the left. So B is guided here. At that instant of 20 degrees, this is given. So if that is so, determine for this position 20 degree orientation, what is the omega AB, angular velocity of this bar, and velocity of this point B. So this would be solved now by a procedure called relative velocity method. So why this is called a relative velocity method, you will understand. This complex general plane motion can be resolved as two motion as translation plus rotation. So how do I consider? I know it is going to be on a horizontal. So what I will do, first I will resolve this motion. So I will look at this bar now as translating bar plus a rotating bar. So rotation will be what? About the point where I know the velocity of the bar. That's what is our relative motion, right? So this is point A, this is point B, and this is point A, this is point B. So what is that is known from the given problem? I know the velocity of this point A to the horizontal. That is VA, that's 3 meters per second. So if this is VA 3 meters per second, and if I consider it's only translating, this point also is with the same velocity. So here VB also will be equal to 3 meters per second. So this is translation alone. You may ask, how can it be possible? It's not possible. We are imagining that the next instant what would happen for that. We assume that this bar is translating like that, and then we take that other component rotating with respect to a contact point A where velocity is known. So this plus, and this is going to be rotating with point A. Because why with respect to point A is because I know the velocity given for point A. So this is my reference point. I know absolute motion of this point A. I do not know absolute motion of point B, but I can relate absolute motion of point B, that is my velocity VB. How? Absolute motion of other point A, VA, plus motion of B with respect to A. Right? Motion of B with respect to A. So B with respect to A, when I look at this, and I know as this angle is going to decrease, the rotation is clockwise. And we have seen in the first hand here I was explaining you, if the bar is only rotating like this, if this is rotating in counterclockwise, velocity is in this direction tangentially. So if you have understood this, then it is very simple here. The velocity of B now, see, with respect to A is right angle to this, and this is velocity of B with respect to A. And this is what is omega AB. So now you look at this one equation brings in the resolution of this general plane motion as translation first plus rotation. So this is rotation. This is rotation, this is translation. No, I am not considering. Right? So now, how do you solve this problem? So look at that, it's very simple. And how this is related, VBA velocity is what? Now, VBA is this point velocity with respect to point A, that would be length of this bar LAB times omega AB, right? So I can get omega AB if I know this magnitude. If I know this and I know already this, I can find out VB magnitude. That's all. So how do I go about solving this? Is solving it by vectorially. I will draw that triangle. So I know point A is now moving to the left with a magnitude of velocity 3 meters per second. So I take the magnitude length and draw this arrow. And I know VB is guided along 30-degree slope. So direction of VB is on this line. I do not know what is its magnitude. This is to be found out. So this is VB. This is VB. But I can find out now. And this is VA. It is given, so 3 centimeter I draw this line, and this is I draw with 30 degrees because point B is here. So this is a vector, velocity vector, and now we have looked at this velocity of B with respect to A. What is its direction to horizontal? What is this direction? So that's what is very interesting here. So if this angle is 20 degrees, this angle is 20 degrees, and this angle to the vertical is 20 degrees. This angle is 20 degrees. That's what you know. You draw a slope and draw a normal. Normal to the vertical is same as that of slope to the horizontal. That's a known geometry. We have been using that in statics, and you have to just recollect. So if this is 20 degrees and this angle is 70 degrees. So the direction of VBA to horizontal is 70 degrees. So that I know. So I will be just marking that here. So direction of that. So I will draw a line from here, because what is my relative velocity concept? VA plus VB with respect to A is what is VB. So this is what we write. So VA is this. I add this vector VBA. So from the head of this, I will draw this vector at an angle 70 degrees here. That's all. So if I draw that, where it intersects, there it ends. So there it ends. So this is point. Now this is VB and this is VBA. Right? So let me erase that excess, whatever is it. So I have it now. So if this is 70 and this is 30, what should be this angle? This angle is 80. So after drawing this vector diagram, I just look at them only by the dimensions, magnitude only. I wanted only the magnitude. So for that I can use this as a triangle law, and I know one side and three angles, so I would be able to find the other two sides simply by sine rule in this triangle. So what is that? So modulus of VB by sine of angle 70, opposite to that is 70, will be modulus of VBA by sine of angle, opposite to that is 30, sine 30. That would be equal to, here its magnitude is 3, so 3 by opposite angle is this, sine 80. So it is going to give me what is my VB. That's one of the question. So VB magnitude will be 3 sine 70 by sine 80. And what is VBA is 3 sine 30 by sine 80. That's all. So if I solve this, I will have 3 into sine 70 divided by sine 80. That's 2.86. 2.863 meter per second. So what is its direction? We know that it is along this, so it is to the horizontal 30 degrees. Yeah. Any doubt? And then this you can get it. 3 into, yeah, I can go. Sine 30 divided by sine 80. So that's going to be 52523. Right? 1 point, just 3 into sine 30 divided by sine 80. That's 1.523 meter per second, and its direction to the horizontal is 70 degrees. This is 70 degrees. So this you have got it. So therefore now omega AB is VBA by length of AB. So you have 1.523 divided by length is 2 meter. So if I divide this by 2, I get 0.761. 0.7615. So 2 radians per second. And what is the direction? Clockwise. So that is all. So any doubt in this solving problem? If you do not have doubt, I'm going to explain you the same problem. We can also solve it by another method called the instantaneous center of rotation method. So